Good day, guys. This is April 8th, 2026 tutorial session. Um, I'm just waiting for more people to join. Today is a tutorial session for students from grade 10 to 12. But anybody's welcome to join the tutorial session. I'm just gonna start. I'll start very soon. Just wanted to. I'm waiting for more people to join. Once I see somebody join. Once I see more people join, then I will start the sharing my whiteboard and start teaching. I'm just waiting for more people to join. And then I'm trying to share it on all platforms. So if anybody have any question, you can put it in the chat box in the comment section. So I'm just going to share my board real quick. Yeah, I believe everyone should be able to see my whiteboard now. So let me scroll down a little bit more. Today is April 8th, 2026 tutorial session. Okay. So I don't have a specific topic I want to talk about, but Okay, I can see there's another person there joining the live session. So if you are a student, you can just put your name and let me know what grade you are in. Whatever topic you want me to talk about, you can put it in the comment section. Um, I'm going to be talking about. I want to talk about forces. Okay. So we know that force, the formula for force is equals to mass times acceleration, right? And the SI unit for force, is Newton. I can see there are 3 people on the live stream. So if you're a student, you can let me know what grade you are in. If you have any questions, you can put it in the comment section. You can let me know what topic you want me to talk about. But if nobody says anything, I'm just going to keep going. And there are 3 different types of forces. Three types of forces. The first one is gravitational force. The second is strong nuclear force. And the third is electroweak force. These are the 3 fundamental types of forces. So, but first of all, I would like to talk about the gravitational force. Let's talk about the gravitational force. Okay. And the gravitational force is connected to a law of Newton's law of universal gravitation. And the Newton's law of universal gravitation states that every particle in the universe exerts an attractive force on every other particle. And a particle is just like a piece of matter that is small enough in size to be regarded as a mathematical point. So, for example, if we have 2 particles that have masses m1 and m2, they are going to be separated by a distance r. Okay, and the force that each exert on the other is directed along the line joining the 2 particles. So the formula that is known for the gravitational force is F equals G m1. Sorry, let me clean this. m2 over r squared. Okay, so m1 is mass of particle 1, m2 is mass of particle 2, r is the radius between those 2 particles, and then g signifies universal gravitational constant. So g is equal to 6.674 times, let me take this off, times 10. Oh, my screen is gone off. Just give me a few seconds, it's going to be back real quick. So we have 6.674 times 10 raised to power minus 11 Newton meter squared per kilogram squared. And this constant G is called the universal gravitation constant, like I said, because it has the same value for all pairs of the particles anywhere in the universe. no matter what their separation is, no matter the distance between those two particles. And the value for G was first measured in an experiment by the English scientist Erin Cavendish. He was the one who discovered this value of G equals 6.674. And then after like 100 years, about a century later, Newton proposed his own law of universal gravitation. So I'm going to draw how this thing works. So for example, let's say there's a small tiny ball here, right? And there's another small tiny ball right here. Okay. So now there's a positive force pushing it to this side, and there's a negative force that is pushing it towards the negative x-axis. So the distance between this is what we call r. Okay. This is the mass of object 1, m1. This is the mass of object 2, m2. And these two particles that has the masses m1 and m2 are attracted by gravitational forces plus F and minus F. And these two forces, they have equal magnitudes and opposite direction, okay? Because they act on different bodies, causing them to be mutually attracted. So they are an action reaction pair. And this is similar to Newton's third law of motion. Newton's third law of motion. Okay, so I know I've talked a lot about this. So I'm going to give an example. Let me just do one example. So example one says that what is the magnitude of the gravitational force that acts on each particle assuming m1 is equals to 12 kg, approximately the mass of a bicycle. M2 is equals to 25 kg and R is equals to 1.2 meters. So using the formula F is equals to G M1 M2 over R squared. So M1 is equals to 12 kg, M2 is equals to 25 kg, and R is equals to 1.2 meters. Okay. So for us to calculate the gravitational force, that will be F equals to 6.67 times 10 raised to power minus 11 Newton meter squared per kilogram squared, okay, times M1 is 12 kg times 25 kg divided by 1.2 meters squared. So let me punch the calculator. So we have 12 times 25 will give us 300. So now we'll do 300 divided by 1.2 all squared. So in this case, we should have 6.674 times 10 raised to the power minus Newton meter squared per kilogram squared times 208.33 kilograms squared per meter squared. So now this kilogram square, we cancel this one. The meter square, we cancel this. So now we have let's do 6.67 times 208.33. So that would be 1390.4 times 10 raised to the power minus 11 Newton. So, but what I want to do is that I want to reduce the negative power. So I can carry this one into three places. So that will be 1.390 times 10 raised to the power minus 8 Newton. Okay. So that will be it for that question. So for example, let me give another example. So we are given that the mass of the Hubble Space Telescope is 11,600 kg. Determine the weight of the telescope. A, when it was resting on the Earth, and B, as it is in its orbit 598 kilometers above the Earth's surface. So in this question, what this question is literally trying to say is that the weight of the Hubble Space Telescope is the gravitational force exerted on it by the Earth. And according to the universal gravitation equation, the weight varies inversely as the square of the radial distance. So we are expecting the weight of the telescope on the surface, on the Earth's surface, to be greater than its weight on its orbit. So now, for us to find the weight of the telescope when it was resting on Earth, we are going to use the formula: weight is equals to G mass of Earth times the mass over R squared. So this is the mass of the telescope. Okay. So we know that the mass of the Earth is 598 kilometers, right? No, that is orbit above the Earth's surface. So the mass of the Earth, let me write it: mass of Earth is equals to 5.98 times 10 raised to the power 24 kg. Okay. And we know that the mass of telescope is equals to 11,600 kg. So if we want to find the weight of the telescope when it's resting on Earth, that will be W is equals to 6.67 times 10 raised to the power minus 11 Newton meter squared per kilogram squared, okay, times 5.98 times, oh, Bennett, thanks for joining. I see you, man. Times 10 raised to the power 24 kg times 11,600 kg, all divided by 6.38 times 10 raised to the power 6 meter, all squared. So now let's try to multiply 11,600 times 6.67 times 10 raised to power minus 11 times 5.98 times 10 raised to power 24. So that will be equals to 4.627 times 10 raised to power 19. So 6.38 times 10 raised to power 6 squared. 6.38. So that will give us 4.0704 times 10 raised to power 13. Okay. So 4.627 divided by 4.0704 is equals to 1.14 times 10 raised to power 19 minus 13 is 6. So this will be Newton. Okay, because this one we cancel this one. These kilograms, when they multiply each other, will be both kilograms squared. We cross out this. So that will be the SI unit there. So now the next question says, determine the weight of the telescope as it is in orbit 598 kilometers above the Earth's surface. So one thing we need to know is that when the telescope is 598 kilometers above the surface, its distance from the center of the Earth is R equals 6 points. So we're going to add up the distance of the Earth radius. So R was the radius of the Earth. We add up the radius of the Earth with the distance that we are given of the orbit of the telescope above the Earth's surface. So the radius of the Earth is 6.38 times 10 raised to power 6 plus we are given that it is 598 kilometers above the Earth's surface. This one here. So that will be 598 times 10 raised to power 3 meters, because this one is also in meters too. Okay. So if we add it up, we should get 6.98 times 10 raised to power 6 meters. Okay. So now the weight now can be calculated in part A. So no, like the way we so now we're going to do W is equals to G M E M over R squared. So it's just the same way we do A, but just that the radius now is different. This is what we are using. In this case, we used the radius of the Earth in part A. So now the gravitational constant is 6.674 times 10 raised to the power minus 11 times the mass of the Earth is 5.98 times 10 raised to the power 24 kg, and the mass of the telescope is 11,600 kg, all divided by 6.98 times 10 raised to power 6 squared. Okay. So the everything on top at the numerator will be 4 point, I don't know what's going on with my pen, 4.627 times 10 raised to power 19. And then let's do 6.98 times 10 raised to power 6 all squared. So that will be 4.872 times 10 raised to power 13. So when we divide it, 4.627 divided by 4.872 will give us 0.95 times 10 raised to power 6 Newton. So that will be the answer for that one. So another relation that I want to talk about is the relationship between mass and weight. Like massive objects weigh a lot on the earth, but we need to realize that mass and weight are not the same quantity. So, for example, let's say for an human being, we don't ask that what is the mass. Although we might say body mass index, right, just to calculate the fat percentage of an individual, but by and large, whenever an individual, we want to record the body mass of an individual, you ask for its weight. Okay, so and the difference between weight and mass is that weight is a vector quantity and mass is a scalar quantity. And what's the difference between a scalar quantity and a vector quantity? A scalar quantity has magnitude but no direction. Okay. While a vector quantity has magnitude and direction. So let me talk about examples of scalar quantity. So the example of scalar quantity is temperature, time, mass, what other thing? Okay, I know there are still more, but I know speed. Yes, speed is a scalar quantity. Speed has magnitude but no direction. Distance, and let me talk about scalar quantity. I mean vector quantity. So examples of vector quantity is weight, acceleration, force. Okay. Displacement, velocity. There are a lot of them. So, but that's the difference is that vector quantity has magnitude and direction. Scalar quantity has only magnitude, no direction. And the formula for weight is mg. So now I'm going to tell you let me talk about the relation between mass and weight now, just like I was talking about before I drifted my train of thought. So the relation between mass and weight is that they are related in two ways. Now, the equation I gave for weight is equals to gravitational constant, the mass of Earth over the radius squared times m. Okay, so let's do like this. So, but now I want to group this. This one, when we group it, if we multiply acceleration due to gravity times the mass of Earth divided by the square of the radius of the Earth, it will give us the value for acceleration due to gravity, which is g equals 9.8 meter per second squared. Okay, so this will be weight is equals to m, this will be g. So this is the formula for weight: mass times acceleration due to gravity. So for example, let me give an example. So if a boy has, sorry, if a boy weighs 50 kg on Earth, what will be his mass? So in this case, we have to find the mass. So the weight is 50 kg, right? Acceleration due to gravity g is 9.8 meter per second square on Earth. And we have to find mass. So from W equals mg, m is equals to the weight over acceleration due to gravity, right? So now his mass on Earth will be 50 kg divided by 9.8 meters per second squared. So 50 divided by 9.8. So that will give us 5.1 kg. Sorry, what's going on with my pen? My screen is off right now. Just give me 45 seconds. It's gonna be back real soon. Just give me a minute. I don't know why my screen is hanging. Okay. So that'll be it for that question. I want this thing to. So let me talk about something that. So, for example, let's say we are given a question. Now, this question is going to be comparing between mass and weight. I don't know what's going on my screen tonight. So let's say, in an example, a vehicle designed for exploring the moon's surface is being tested on Earth. Where it weighs roughly 6 times more than it will on the moon. It says that the acceleration of the vehicle along the ground is measured. So to achieve the same acceleration on the moon, will the required force, will the required net force be A, the same as that on Earth, B, greater than that on Earth, or C, less than that on Earth? Sorry, my phone went off. Let me just check real quick. So in this case, the question says a vehicle designed for exploring the moon's surface is being tested on Earth, where it weighs roughly 6 times more than it will on the moon. The acceleration of the vehicle along the ground is measured. To achieve the same acceleration on the moon, will the required net force be A, the same as that on Earth, B, greater than that on Earth, C, less than that on Earth? So one thing that you need to know is that we should not be confused by the fact that the vehicles weighs more on the Earth, because the greater weight occurs only because the moon because the mass and radius of the Earth are different from the mass and radius of the moon. So in any event, Newton's second law, the net force, it says that the net force is proportional to the vehicle's mass and not its weight. So if we are relating it to Newton's second law of motion, Newton's second law of motion says for a given acceleration, the net force depends only on the mass. So if the required net force is greater or smaller on the moon than it is on the Earth, it means that the vehicle's mass is different on the moon than it's on the Earth. So in this case, we will say that B and C is not correct. So that means that the required net force is not greater than that on Earth and is not less than that on Earth. So therefore we say that for us to achieve the same acceleration on the moon, the required net force needs to be the same as that on Earth. So in this case, we know that the net force summation F, I don't know, my pen is not writing. Just give me 30 seconds. Summation F is equals to mass times the acceleration, right? So the net force required to accelerate this vehicle is based on this Newton's second law of motion, where m is the vehicle's mass and a is the acceleration. So for the given acceleration, the net force depends only on the mass, so which is the same on the moon as it is on the Earth. So therefore, we can say that the required net force is the same on the moon as it is on the Earth. So I'm just going to move on to a new topic. I believe that I've talked about gravitational force a lot. So I think I will just talk a little bit on projectile motion. So in projectile motion, the video I dropped today. I did some examples on projectile motion. Okay, so I'm just going to give one example. So example, find the range of a projectile motion with a velocity of 5 meters per second, 15 meters per second at an angle that is shot at an angle of 30 degrees. Okay, so the formula for finding the range of a projectile motion is R is equals to U square sine 2 theta over G. R is equals to U square sine 2 theta over G. So the range, the velocity is 15 squared sine 2 times 30 over G is acceleration due to gravity is 9.8. Okay, 15 times 15, which will give us 225 sine 60 degrees divided by 9.8. So if we do 225 divided by 9.8 is equals to 22.96 sine 60. So 22.96 times sine 60 is equals to 19.9. Sorry, let me write it properly. It's been 19.9 meters. Okay. So if we are asked to find I want us to find another one. So let's try and see if we can find the time of flight and let's find the time of flight and maximum height. So if we want to find the time of flight, so the formula for time of flight, right, will be t is equals to 2u sine theta over g. So this is the formula for finding time of flight. Okay, so we know that the velocity is 15, right? So that will be 2 times 15 sine 30 degrees divided by 9.8. Okay, so 2 times 15 is 30. So 30 divided by 9.8 will be 3.06 times 3.0612 times sine 30. So if we do it times sine 30, it will give us 1.53. So sine 30, I believe, is 0.5. So that would 1.53 seconds. Okay. So now if we wanted to find the maximum height, the maximum height h, the maximum height h is equals to u square sine squared theta over 2g. So the u squared, which is the velocity, is 15 squared times sine 30 squared over 2 times 9.8. So 15 squared is 225 times, I believe, sine 30 is 0.5. So 0.5 squared is 0.25 divided by 19.6. So 0.25 times 225 will give us 56.25 divided by 19.6. That will give us 2.87 meters. So that will be, I dropped a video on projectile motion. You guys can check it out. And I'm going to be doing much more difficult word problem questions on projectile motion. I'll be dropping that video on Friday. So that will be all for today's session. Let me just go back. So I appreciate everybody. I appreciate everyone who joined today's tutorial session. So stop sharing. So that will be the end of today's session. So if you have not subscribed to my channel, please make sure you subscribe. Make sure you like the video. And for my other videos, you can also share to those who are not aware about my channel. And that will be all for today. Thank you guys. Peace out. Have a blessed evening.